And good afternoon, good evening to everyone joining. Welcome to the first episode of the SaaS Academy Tech Track. In this episode, we will be talking about breaking down the monolith in your SaaS application. Please check in on today's event if you have not already done so. The check-in link is on the screen, which is aka.ms/reactorcheckin. And please use the event ID 14561. By checking in, you get access to all the resources and learning paths after the event. The check-in information will also be added onto the chat. My name is Rav, and I'm the Program Manager at Reactor London. You can find all the events related to SaaS Academy Tech Track on the Microsoft Reactor website. Before we get into the session, please take a moment to read our code of conduct. We are all here to learn, so please be respectful of other people's views, understanding of differences, and be kind and considerate in the way you engage. The chat will be open throughout, and we do encourage you all to participate. And with that, I will now hand over to Pablo, who will introduce the SaaS Academy Tech Track.
Hi, everyone. Welcome to SaaS Academy. I'm Pablo from the UK Azure Business Group, and it's very great to have you all here. So SaaS Academy was inspired by our CEO's vision, Satya Nadella, that every company will become a software company. We're here to help you build and scale your SaaS solution, and it is your chance to deep dive on Microsoft technologies, learn more about the future of SaaS, learn about experts, partner, and customers on how to do so in the full journey. This is a joint program brought to you by Microsoft Western Europe, Microsoft UK, and the Microsoft Reactor. So special thanks to Dorian Cohen, Irina Costina, Sherry List, Gonzalo Ruiz, James Woolard, and Rav Cocker that have made this possible. So before I introduce our distinguished speaker, Paolo Salvatori, he'll be addressing how to break the monolith in your SaaS application. I wanted to share a quick video on what the SaaS Academy is. So Rav.
Did you know that every business will eventually become a software business? Microsoft CEO Satya Nadella not only made that prediction, but also continues to lead Microsoft to SaaSify its portfolio. With SaaS solutions, you can grow your business and make even sophisticated enterprise applications like ERP and CRM affordable if you lack the resources to buy, deploy, and manage your infrastructure and software. So, how to get started with SaaS? That's why we created the Microsoft SaaS Academy. It is your chance to deep dive into the latest Microsoft technologies and learn more about the future of software as a service from Microsoft experts, partners, and customers. Our SaaS Academy was designed with a business track and a tech track to provide companies like yours with the SaaS knowledge that fulfills their needs. Our business track covers the SaaS fundamentals, whether you are a cloud-native company or a traditional software provider, while the tech track addresses technical aspects of building a SaaS solution, including SaaS architecture, DevOps, and sustainable software engineering. You can get started with SaaS in the same time it would take you to build a Microsoft PowerPoint about it. Ready to accelerate your journey to SaaS? Don't miss our upcoming webinars and join the Microsoft SaaS Academy now.
Perfect. So about our speaker today, Paolo Salvatori is a principal system engineer. He's been at Microsoft for 24 years, and he's been part of different teams, including Microsoft Services, the BizTalk server team, Azure Customer Advisory Team, and he most recently joined the Fast Track for ISV startups team. Paolo collaborates with both enterprise and ISV customers to design and implement cloud solutions on the Azure platform. He focuses on resilience, scalability, and security. He also actively creates guidance, samples, and projects, such as the Service Bus Explorer tool, which is in the official Azure documentation and GitHub repositories, and we'll be sharing that later in the talk as well. So without further ado, Paolo, thank you so much for being here. Over to you.
Thanks, Pablo. So let me share my screen. And all right. So thanks, Pablo. So as Pablo said, I am a principal system engineer in the Fast Track for Azure ISVs and startups. So my team works with ISVs every day. And in this presentation, we included some of the real world experience they were making every day with our customers. So the agenda is quite rich. So I will try to go quick. So we'll start introducing the cloud journey. What is a monolithic application? We'll cover what is a microservice-based applications, what are the advantages over a monolithic application. We'll introduce the concept like API gateways, containers, and Kubernetes, which are the fundamental components of microservice-based applications. We'll touch on tenancy models. We'll see what are the tenancy models that you can use. And finally, we'll talk a little bit about multi-tenancy in Kubernetes and the reference architecture with Azure Kubernetes Service. So let's get started talking about the journey to the cloud. This slide represents the typical journey to the cloud of ISVs and customers. So usually the first step consists in migrating an existing on-premises application to the cloud. And this is done typically by rehosting the application on infrastructure as a service VMs. So in this case, the application has almost no changes, doesn't have any record, simply hosted on VMs in the cloud. The next step is to turn the monolithic application in a cloud optimized application. So still without re-architecting or altering the code in a significant way, ISVs can gain additional benefits just from hosting their monolithic application in a PaaS service like app services and web apps, or eventually in a container instance. At this step, sometimes customers are also taking the chance to containerize the application. While talking about the database, they usually improve the agility and the of their application, just hosting their database into a PaaS service like Azure SQL database, because this way they can get advantage of built-in features like automatic backup and restore and patching. So the next step and the final destination in some way is to make the monolithic application and cloud native application. This usually requires a major refactoring of the application, because you have to break down the monolithic application into multiple microservices, each using a separate database. So this table basically has been created, putting together the experience we made with many ISVs that made the journey from the typical lift and shift approach to a cloud native approach. As we said before, usually the first migration step consists in hosting single tenant architecture on VMs. So ISV typically create a single tenant deployment for each of their tenant when, for example, providing a SaaS application. This is done in a dedicated subscription one for each tenant, and they are hosting the monolithic application on a VM while hosting the database that typically is a SQL server or a PostgreSQL, a MariaDB or MySQL on another VM. The next step is moving the monolithic application with very little code changes to Azure App Services or container instance or even Kubernetes, because, for example, you can also containerize, as we'll see, an existing monolithic application and run it on a container orchestrator. The final step is to containerize, to break down the application and create containerized microservices, or eventually you could also use a different application architecture style that is a serverless. In this case, you can use Azure Functions. But in any case, this journey requires a deep cultural change, because the organization need to adopt new ways of breaking down the work across multiple teams. They have to use new tools, new processes. Monolithic application actually is. So a monolithic application is a single tier software application in which the user interface and data access code are combined into a single program from a single platform. Another definition basically says that a monolithic application is composed of multiple modules or multiple tiers and so forth. In reality, as you can see on this picture, there are several kinds of definitions and architectural style for a monolithic application. Some cases is a multi-tier application with a presentation, business logic, and data access tier. All of these architectural styles, they share the same characteristics. That is, all of the subsystems, they share a single relational database in many cases, and the deployment of all of the artifacts is a single unit of work. Now, talking about pros and cons of a monolithic solution, the advantages are an easy development and deployment model, and for sure also performance, because think about an online store with different subsystems like the product catalog, the ordering system, the basket system. In many cases, these subsystems are just running within the same process. So cross-subsystem calls are just, in-process method calls. So they are fast by nature. On the disadvantages side, we can mention that individual parts of the system cannot be scaled independently because all of the subsystems are running in the same process, and so they are tightly coupled. For the same reason, scaling out a monolithic application can only be accomplished by cloning the whole application. And it's also very hard to maintain. Think about a situation where you have a shared library, for example, for the data access, that is used by multiple subsystems. In that case, any change to that library or to the underlying schema of the database has an impact on all of the subsystems using this library or schema. And then you have multiple teams also working at the same code base in parallel, and then can introduce some challenges. So is monolith bad at all in general? No, it's not. So there are many examples out there in the real world of very successful applications that still have a monolith application style. For example, on this picture, you can see a typical online store where all of the modules like identity, catalog, ordering, basket, and so forth are running within the same process, within the same application. Eventually, the application can be, divided into tiers, but they're all sharing the same relational database that is used to provide data consistency. In front of the application, you can also have a REST API that is invoked by a mobile app, or you have a web app that it provides an HTML interface, or you can even build a single page application with .NET, with using a web framework like Vue or React or Angular. So the message and the suggestion is that you should adopt microservices only if they bring you some competitive advantage in terms of flexibility, agility, cost savings, time to market, and not just because Kubernetes is the new black, everyone uses Kubernetes, so you want to use it. So what is a service? Let's start by introducing what is a service before talking about, microservice architecture. So a service is just a piece of code that solves a very domain-specific problem. So for example, it's a component and a service that is used for all of the functionalities of a product catalog, subsystem, ordering system, or a basket system, for example. This is typically built by a small team of people using a very specific technology stack, and all of the services doesn't necessarily need to use the same technology stack. So one service could be written in Python because it makes sense to write that piece of code in Python, while another service could be written in .NET Standard, for example. So all of the services expose features to callers using a very well-defined API that represent a contract between the service and the client application. As we'll see, you can use different technology. You can use a REST API, you can use Graph API, you can also use gRPC to expose these functionalities. Typically, the services degrade in a graceful way when they depend on other services. You can use very solid design partners like Circuit Breaker to implement this behavior. Very important characteristic of a service, they can be upgraded and scaled independently of other services. This is one of the more important tenets of services and microservices. What is a microservice? So a microservice-based architecture is an architectural approach for building a server distributed application as a set of small cohesive services. Each microservice runs in its own process or container and communicates with other services using transport protocols like HTTP and REST, or WebSockets, gRPC, or using volatile or persistent messaging system like Service Bus, ZeroMQ, RabbitMQ, and so forth, using transport protocols like AMQP or MQTT. Now, each microservice implements a specific end-to-end domain or business capability. Again, let's make the sample of an online store. So a typical example could be the basket microservice, the user profile microservice, the product catalog, and so forth. They can be developed autonomously by separate teams and independently deployed of each other. Each microservice should own its related domain data, should encapsulate this data, and also the domain logic to handle those data, and could use also different data repositories. So one microservice could use under the cover Azure SQL database, while another one could use a NoSQL database because it makes more sense to use a NoSQL database like MongoDB, Cosmos DB, Cassandra DB, and so forth. And as we said before, they could also use different programming languages. Now, what is the process that you can use to model and identify microservices? You can use a domain-driven design approach and bounding context to identify a set of loosely coupled microservices. You can proceed this way. You start from the business domain of your solution, and you start writing down functional and non-functional requirement. You come up with a high-level description that you can refine to individuate data domain. In this case, then the next step is to define bounding context for each of these domains. And then for each domain, you can define entities, aggregates, and services. Then you can use these analyses to identify microservices. Now, you can find there is an entire literature around, the way you can define microservices. There are very good books, and I can even, if you ping me, I can send you some links. In a nutshell, this process is an iterative process, so it's an ongoing process. Microservices are not written in stone. You can eventually, refine the model and eventually aggregate existing microservices, or do the opposite and split up microservices into smaller services. So once again, microservices are independent piece of code that maintain their state. They are generally developed by a small team, and they can use different frameworks and technology stacks. They are loosely coupled. They communicate over very well defined interface and protocols. They are identified by a URI that can be used for service discovery. And once again, they can be independently updated, version deployed, and scaled. So this slide provides 4 reasons why you should switch from a monolithic application to a microservice approach. Think about a photo share service like Pinterest, for example, where users can upload pictures. For example, under Christmas or during summer, when there are a lot of users publishing pictures, you may want to scale out the thumbnail service that is invoked by the photo share service. And then when this period is over, okay, and the traffic is lower, you can eventually scale in the number of instances of the thumbnail service. So as you can see, that these 2 services scale in an independent way. You can use different technology stacks. So the photo share service could be written in Node.js, while the thumbnail service could be written in .NET Standard. They can also be independently versioned and deployed. Let's say you are making a change to the thumbnail service to add a new functionality, or just because you are using a newer version of a component of a library, you can just deploy a new version. And as far as the thumbnail service maintain the contract, the interface exposed to the photo share, this is fully transparent to the photo share service. The 4th reason is to eliminate conflicting dependencies. Think about a scenario where you have inside the same process 2 different subsystems using 2 different versions of the same library. This, let me say 10 to 20 years ago was called the DLL hell, right? Now this is, solved by breaking down the process into smaller services. At this point, every service can use a different version of the same library. All right, so let's talk about deployment approach. So in a traditional monolithic approach, the only way to scale out a monolithic application is by cloning the whole application across multiple physical servers or VMs. So these bring to a very coarse grain density, while, for example, in a microservice approach, the functionalities are segregated into smaller services, which makes the deployment much more fine-grained, and in this allows to have a better density, because on the worker nodes, for example, of a Kubernetes cluster, you can host more containers, more applications, basically. And so architecting fine-grained microservices-based applications also enables a continuous integration and continuous deployment best practices, because you can, as we say, deploy services or updates to services in a more agile way, because whenever you make a change to a service, you only have to deploy that service without redeploying the entire application. Talking of data, in a monolithic approach, many monolithic applications, use a single centralized database, or just a few databases that are shared by multiple tiers and subsystems. And this approach has some advantages, because for sure achieving data consistencies is much easier, because even if different subsystems are using different tables in the same database, think about the product catalog, the basket subsystem, and so forth, you can use ACID transactions across multiple tables. Okay, this is not possible when using a microservice-based approach. But on the other side, there are also some disadvantages, because when using a single database, the database, especially if your application is very successful, it becomes very huge, especially if you don't use any kind of vertical or horizontal partitioning, which means that this is going to slow down the system, especially if you have multiple subsystems all accessing in a read-write mode the same tables. And furthermore, if you have some batch processing going on, these can also interfere with the performance of the application. So these are the reasons why it's in a microservice approach. Every microservice, regardless if it's stateless or stateful, has a different database behind the scene. Now, each microservice owns its domain, data, and logic. This data, the data that is owned by each microservice, is private to that microservice, which means that other microservices cannot directly access the tables or in the database of another microservice. So for example, in the picture, you see that the catalog microservice cannot access the basket table in the basket DB directly. It can only send a request, so a request response request, or an asynchronous message to the basket microservice. So microservices are loosely coupled, and they should be able to evolve in an independent way. These apply also for the schema of their databases. So if you make a change to the schema of the basket database, this doesn't have to have implications with on other microservices. This is why every microservice owns and encapsulates its database. So as we said, there is no direct access to the database from another microservice. The transactions against a single database can use ACID transactions. So the basket microservice can use local ACID transactions against the basket database, but there are no ACID transactions across microservice databases. So just for clarity, ACID stands for, as you know, atomic, consistent, isolated, and durable, that are the typical characteristic of transactional relational database or form. So in case of microservices, you have to use an eventual consistency model when your application is made of multiple microservices. And these pose some questions, because this approach is much harder than using simple SQL joins across multiple tables. First thing, you don't have integrity constraints between tables like foreign keys in a relational database. You don't have distributed transaction across multiple databases. You don't have two-phase commits. So how can you solve and achieve data consistency across multiple microservices? Well, you can use, for example, the Saga design pattern. That is a way to manage data consistency using an eventual consistency model across multiple microservices that compose a distributed application. So a Saga is just a sequence or a workflow of local transaction, each updating the repository of a microservice. And every microservice has the responsibility to send a message or event, okay, to notify other microservices that the transaction completed with success or with a failure. So if a step fails, the Saga should execute so-called compensating transactions to basically undo the work that has been done so far by the preceding transactions. There are two different types of Saga design patterns. One is called choreography. In this model, all of the services participate to the decision-making process. And so all of them start executing a local transaction. When it completes, the first one sends an event to a message broker. The message gets received by the other microservices. Based on the outcome of the previous transaction, the second service could decide to go on and execute the local transaction. And in case it fails, you could send back a message to the message broker to notify the other services, which are going to execute a compensating transaction. Vice versa, if the transaction successfully completes, it can proceed with the third one, and so forth. So this model is a good fit for distributed applications with a low number of microservices. If instead the topology of the microservice-based application is more complex, it's much better to use an orchestration model. In this case, there is a centralized controller or orchestrator that tells all of the Saga participants, so the microservices, what are the local transactions that they have to execute and in which order. So it's responsibility of the orchestrator to handle, all of the transaction and keep the intermediary state, and eventually, tell all of the microservices to run compensating transactions if something goes wrong. All right, so let's move on. So communications. So of course, you also want to make sure that microservices can communicate with each other. So let's divide communication in two different categories: synchronous versus asynchronous, single receiver versus multiple receiver. So synchronous communications are based on synchronous protocols like HTTP. In this case, the client application typically sends a request to a service and waits for a response before it can continue with its processing. In asynchronous processing or asynchronous messaging, application typically communicates with messages or events sent through volatile or persistent messaging system like Azure Service Bus or EventID on the Azure platform, but you can also use open source messaging system like RabbitMQ, ZeroMQ, ActiveMQ. You can also use Redis Cache that internally provides a PubSub engine. So in this case, the client code sends a message or an event and doesn't wait for a response. When each request, so in a single receiver mode, each request must be processed by exactly one microservice. In this case, typically this kind of communication is used to send a command to another service in an asynchronous way. So the sender is expecting that the receiver is doing some action and eventually comes back with another message to send back a response in an asynchronous way. One-to-many communication instead are typically used by microservices when they want to notify that something happened within their domain. And they don't even know which microservices are going to receive this notification. This event that is not a command, it's just a notification, and as such can be treated in a different way by every receiver. So in this case, the message can be received by zero or multiple receivers, depending on the filter expression they specify in their subscription. And this is the typical example of a PubSub design pattern that is used by event-driven architectures. So the advice here is to minimize the communication between separate microservices, because again, and avoid as much as you can synchronous communications, because if you have a chain of synchronous code, this is going to slow down your system, because the initial caller has to wait for the completion of the chain of synchronous calls. Like if the client application invokes a microservice in a synchronous way, which in turn calls another service in a synchronous way, and so forth. It needs to wait for the completion of all of these calls. So this kind of chain should be avoided as much as you can. So these are four examples of communications across multiple microservices. The first one is the typical example of a client app that uses the request response communication style to make a request to a couple of underlying microservices, the catalog and the basket in this case. So in this case, you are using an API gateway microservice that is used to send individual requests to the two underlying services, the catalog and the basket, aggregate results, and send back a response to the client mobile app. In the second example, you can see a service sending some contents to the client application that are connected at that time. For example, on this slide, we have two web app single page applications to send some, content, some data, some events using WebSocket and SignalR. The third one is a typical single receiver message-based communication, where, for example, in this case, the basket microservice sends a message in an asynchronous way to the ordering microservice. This message contains a command. So in this case, the microservice, the basket microservice, is expecting the ordering microservice to do something. Okay. As you can see, also they are using different databases. So because, for example, the basket is using some cache. It could be Redis cache. And the other one is using a database, could be a relational database like SQL, PostgreSQL, or MySQL. The last example is the typical pub/sub scenario, where a microservice publishes an event to notify other microservices that something happened in its domain. So it could be, I don't know, a product catalog that want to signal the basket microservice that the price of the product item has changed. So it should, change the price in all of the baskets that have that item inside. Could be an example. All right, let's move on. You already have seen in the previous slides the API gateway. What's the API gateway and why it's so important in a microservice-based architecture? Now, every microservice exposes a set of very well-defined endpoints using REST API, Graph API, gRPC, whatever. Now, the API gateway, in some way, is the equivalent of the facade design pattern for the object-oriented programming. So it's basically, it's a service that is in between the client application and the microservices, and is a sort of reverse proxy routing requests from client to services. But in the middle, they can, implement some cross-cutting concerns, such as SSL termination, request redirect, authentication and authorization based on JSON web tokens against an identity provider like Azure Active Directory, but it could be also third-party identity provider like Facebook or Google, for example. They can be used to allow or disallow incoming calls based on some IP lists. They can also be used for throttling incoming calls, or logging and monitoring requests, or response caching, and so forth. So the advantage of using an API gateway, as you can see at the last point, is that you don't have to re-implement these behaviors, these cross-cutting concerns in your code. You can just rely on an application gateway. And this is super important, especially when you are using microservices written in different technology stacks. Because if you are writing microservices using different programming languages, you always have to use different libraries to implement the same concerns like authentication, caching, SSL termination, and so forth. If instead you are using an API gateway, this is provided by the API gateway, and is fully agnostic with respect to the programming language you use to implement your microservices. But the most important thing when using an API gateway is to decouple your client applications from the underlying microservices. Because if you let your client application to directly involve microservices, you are coupling your client application with the microservices. And when you, for example, have to change the interface that is exposed by a microservice, this requires also to change the code of the client app. Instead, if you introduce a level of indirection and you are using an API gateway between the client app and the microservices, you can even change the implementation or even the interface of a microservice. In case of a SaaS application, this also add a partial benefit, because if you front your monolith application with an application gateway, you can start breaking down the monolithic application and gradually replace subsystems like the product catalog, the shipping system, and so forth with microservices without violating the contract with client applications. You can reduce the chattiness, because if a single page or screen of a mobile app needs to retrieve data from multiple microservices, you can just implement, as we've seen in the previous slide, a microservice that simply receives the requests, send individual requests to underlying microservices, aggregates back results, and send back, a response message to the caller. Finally, security issues, because if all of the microservices are directly exposed to the public internet, this makes the attacker surface larger. So these are typical examples of API gateways. So you have a reverse proxy like NGX, HA proxy, and traffic. You can install them on dedicated VMs or run them as containers on Kubernetes. If you are using a service mesh like Linkerd or Istio, you can use the ingress controllers that provides basically the same functionalities like HTTP redirect or SSL termination retries. Or you could use, the managed services on the Azure platform, like the Azure Application Gateway, which is a regional, fully managed layer 7 load balancer that provides, support for many different features, like including SSL termination and a web access firewall. Or from door, there is instead a global layer 7 load balancer. They use the same global edge network used by the Azure CDN, which provides pretty much the same features, but at the global level. So SSL termination, response caching, web access firewall at the edge, and so forth. Finally, you can use API management, which is a turnkey solution for publishing your REST API to both internal and external applications. And again, it provides many features for example, for rate limiting, IP restriction, authenticating and authorizing incoming calls based on JSON Web Tokens, and so forth. So what is a container? You should know by now. It's a lightweight standalone executable package which contains your app, but also everything that is used by your app, so like shared libraries or system tool and so forth. Important thing is that a container is not a microservice. You can use containers to host monolithic applications. So I have some customers, for example, that migrating an existing application, they containerize an existing ASP.NET application in a Windows container, and they're running these on Kubernetes, okay? And a microservice doesn't need to run in a container. I have other customers that instead of using Kubernetes, they are using Service Fabric for hosting their microservices, and their microservices are not containerized. Now, containers are immutable by design. This means that anytime you make a change to a containerized application, you have to delete the existing container and redeploy and replace with a new version of the container. But they provide better density because on a single VM, you can run multiple containers. So what is Kubernetes? Probably you know what is Kubernetes, so I will give you a quick definition. So it's a container orchestrator, is an open source product that can be used to automate, let's say, all of the plumbing for running containers like deployment, scaling, management, observability, and so forth. Kubernetes is a project is part of the Cloud Native Computing Foundation. On the bullet list, you can see all of the features provided by Kubernetes, like scheduling containers across the worker nodes based on the resource requirements and constraints that you can specify using node selectors or tains and so forth. You can automate changes using rollout and rollbacks. You can it can be used for service discovery and load balancing if you are using ingress controller like NGX ingress controller or the application gateway ingress controller. You can also use Kubernetes to mount volumes from different storage systems, especially now using CSI drivers. You can also use Kubernetes for secrets and configuration management, even if the advice on the Azure platform is to keep sensitive data in Azure Key Vault, and so forth. There is a long, long list of features. So the important thing is to understand that the Kubernetes ecosystem is very, very rich. And this is why at the beginning of this presentation, I say that in order to migrate from a monolithic approach to a microservice-based approach, you need to make a cultural change. You need to ramp up new technology. You need to have new skills in your organization. So you need, for example, Docker. Docker is used to build, deploy, and manage containerized applications. You typically use Docker to create container images and publish them to a container registry like Azure Container Registry or Docker Hub. You can use service proxies. In this case, you can use, for example, NGX, HA proxy, and traffic or application get ingress controller. They run as containers on Kubernetes and provide typical features of an API gateway that we have seen before. Service mesh, there are tools that provide, additional features like observability, security, mutual TLS between microservices. And this is done only by injecting a so-called sidecar container in the pod hosting your container. So in Kubernetes, a pod is a sort of a small environment which can contain one or more containers. So service mesh are injecting this sidecar container that intercept all the incoming and outgoing traffic, and this way can implement, design patterns like timeout, retry, secret breaking, and so forth, and observability. So you don't have to implement this stuff in your code, regardless of what is the programming language you are using for your microservice. And this is absolutely great. So some samples of service mesh are Istio, Linkerd, Open Service Mesh, Consul. There are tons of service mesh. For monitoring and observability, the majority of customers are using Prometheus, Grafana, and Jaeger because they are open source, but they're also using systems like Datadog, for example. While for packaging and distributing their application, they are using mCharts, but they can also use Customize, for example. So mCharts are, a way to package, install, and upgrade very complex Kubernetes workloads and their dependencies. Think about a scenario where you want to ship and install your application, but along with a Redis cache, you can add a Redis chart within your mChart so that Redis cache gets deployed with your application. GitOps is a new way of implementing continuous deployment. Honestly, this would deserve an entire session. So in this session, I am just, limiting myself to mention the two most, adopted frameworks, very popular, so Flux and Argo CD. So coming to our offering on the Kubernetes landscape, we have Kubernetes on Azure. That is a fully managed Kubernetes service. We manage for you the control plane. So the only thing you have to look after are the worker nodes. We fully automate, management and maintenance tasks like agent nodes, patching. And the AKS service is free. You only pay for the agent nodes that you use. You don't pay for the service itself. Okay, so you only pay for the VMs that compose your clusters. But you can also use Azure Arc Kubernetes. This is a great way to integrate Kubernetes clusters that are hosted on premises or another cloud platform outside of a Microsoft Azure platform. I work, for example, with a customer that would like to have a single pane of glass where they can see the Kubernetes clusters on Azure, so AKS clusters, but at the same time also the Kubernetes cluster that some of their customers have on-prem, or some Kubernetes cluster that are on other cloud platforms. And you can use Azure Arc to monitor these clusters as well as deploy workloads using GitOps and using Azure policy. So let's, in the last few minutes, let's look at the multi-tenancy models. There are many different multi-tenancy models. They can be, at different levels. So security, because if your infrastructure is shared across multiple tenants, you need to be careful. When accessing data, you don't want to return data of one tenant to another tenant, especially when the same database is used across multiple tenants. Costs, because if you are sharing the same infrastructure across multiple tenants, these can bring some lower total cost of ownership. Performance, because if some customers are consuming more resource than others in terms of CPU and memory, you can, have the so-called noisy neighbor problem, and some, other tenants could suffer these. And reliability, because if you are sharing the same infrastructure across multiple tenants, a problem that affects one of the tenants can result in an outage for other tenants. So let's see what are the deployment models. You have a single deployment model where a single tenant deployment, you have a dedicated set of infrastructure for each service, for each tenant. This provides better tenant isolation, easy to charge back Azure costs to tenants, and reduce risk of data leakage because data is hosted in separate databases, and no noisy neighbor issue because you are using separate resource. On the multi-tenancy deployment model, you see that all of the tenants are sharing the same computing resource and data repository. So you have benefits in terms of cost efficiency and better density, but of course you have a lot of risks from noisy neighbor problem as tenants are sharing the same resource, or tracking back Azure costs to tenants. You can also have, let's say, some trade-offs. So in the first case, in the vertically partitioned deployment, you can have a mix of single tenant and multi-tenant deployment. And this is good also because you can provide multiple pricing tiers for tenants. For example, if you have a tenant that needs a higher level of performance and data isolation, you can deploy a dedicated environment for these tenants. Or you can use an horizontally partitioned deployment approach where, for example, all of the tenants are sharing the same computing resource, like the Kubernetes cluster, and you have, in this case, you can mitigate the noisy neighbor problem. Now, very quickly, and we are approaching to the end, Kubernetes and multi-tenancy. So Kubernetes provides many features to build multi-tenant for multi-tenancy. So you can use a multi-tenant Kubernetes cluster as an alternative to managing many single tenant cluster, one for each tenant. For example, you can, as you can see in this picture, you can deploy individual tenant application in their own namespace. And when they deployed in their own namespace, you can use Azure Kubernetes role-based access control and network policies to segregate and isolate these namespaces from a security and networking perspective. For example, a microservice in one namespace cannot invoke a microservice in another namespace. You can use limit ranges and resource quotas to avoid the noisy neighbor issue because you can basically constrain the amount of CPU and memory that every namespace can use. You can enforce safeguards and security standards using policies like Open Policy Agent and Azure Policy. And then you can use horizontal pod autoscaler or the Kubernetes autoscaling to basically scale out and scale in the number of pods of tenant applications and the number of cluster nodes. All right, so to conclude, we don't have time to go into details, but I invite you to go to the Azure Architecture Center and consult and review these two reference architecture that are based on AKS, or Azure Kubernetes Service. As you can see, there are many moving parts in this architecture, like application gateway, the Azure firewall, the Azure Key Vault for sensitive data, the Azure Container Registry for container images. These are the references that I use to create this presentation, and up to you, Pablo.
Perfect, Paolo. Thank you very much. So we have little time and a few questions. I just wanted to quickly go over, if you want to contact the SaaS Academy team and you have more questions, you want to know more, you want to know how to partner with Microsoft, please contact us at microsoft.com. We're also recording all of these webinars, and we'll go through the whole customer journey on building and scaling the SaaS solution. So feel free to visit our website on aka.ms/SaaS-Academy. And you can also give us feedback. So either scanning the QR code on the screen or visiting the URL we have there. Additionally, if we flip to the last screen, Paolo, on the presentation.
Yes.
We also have coined some one more, sorry. Yes, we have coined NFTs. You can get by visiting and going through the SaaS Academy. So as well, please feel free to scan the QR code and collect the Azure Heroes. So we have 4 minutes. I'll just pick one question and we can follow up with the other ones via email. So there's a question from Rob. What are some tips you can share on how to secure microservices-based application, Paolo?
Yeah, absolutely. I think it's a great question. So first thing, there are multiple levels. So first, for sure, you should use the API gateway, as we said, in conjunction with a web access firewall. And so you could use OWASP rules or custom rules to restrict the access to your services. That's one of the things. You should definitely use SSL termination and use HTTPS. On the Azure platform, you can also eventually front your services using the Azure firewall, because the Azure firewall provides, mitigates attacks from some very well-known malicious public IPs and domains. So you can basically block incoming calls. Same story with the web access firewall. If you are using the web access firewall provided by Azure, the Azure Front Door or Application Gateway, you can block incoming calls that are malicious attacks. And finally, you can also configure the so-called DDoS protection standard on the virtual network hosting your AKS cluster.
Perfect.
I can also pick another one. So
yeah,
because I think it's an interesting one. Docker is no more open source. Microsoft has any recommendation. That's a good one. And this is also one, for example, starting from version 1.19, even Kubernetes is no more using the Docker runtime. And if you go and check the Kubernetes documentation, you will see that now the runtime is the containerd runtime for running containers, which means that you can continue to use Docker on your development environment to be container images, but is no more used by Kubernetes inside. Okay, so that's the point. So in a nutshell, using Docker is no more necessary. Okay, you could use containerd even. What are some tips you can share on how to secure? Okay, why do Microsoft needs a system like microservices system? Well, honestly, Kubernetes is just the most successful container orchestrator. So it became a best practice. As I said before, it's not required that you are running microservice inside containers. It's not strictly required that you are running microservices in Kubernetes. You could even use the same approach and host all of your microservices as separate app services on Azure, for example. That's it.
Perfect. And if you're okay, Paolo, just one more question before we wrap up. How can you evaluate the cost of decoupling against the benefits? Where can I begin?
That's a great question, I think. Yeah, in my opinion, you should always find the right trade-off, because a common question is how small should be my service, for example. Okay, so what is the granularity of your services? In my opinion, you should find the right trade-off. This is why it's important that you are using, a strategy like the domain-driven design to properly, define your microservices. Because as we have seen before, using a microservice approach has some advantages, but regarding data consistency, it poses some, problems because you have to use an eventual consistency model. So
Perfect.
there is no golden rule, and this is why I my advice is go and read the entire there is an entire literature about how to design microservice-based applications.
Perfect. Paolo, thank you so much for being with us and sharing this knowledge. And thanks everyone for attending the SaaS Academy. See you very soon. Our next webinar will be in November. And you can also see the on-demand sessions in our website. So hope to see you very soon. Thanks, everyone.
Thanks, everyone.